Hello! With Advent of Code 2024 fast approaching, I've decided that I will review my 6502 ASM solutions for Advent of Code 2023. I only did 5 days in total because the 5th day started, well, the 4th and 5th days took a very long time to do. But I learnt a lot from those few days. I'm not very good at 6502 ASM. I'm still learning. I'm sure there are some very, very cringe things that I did. And I'm sure that anyone watching this who knows ASM will be somewhat angry. But that's alright. That's okay. I'm learning. It's all a big game for everyone. So, first, let's go into my code. I'm going to start with all of the code that is the same between the days, all the support code. As a good programmer, I'm going to start with that first, and let's open that up. Alright, so what I have first are all my includes, right? I'll come over these a bit later. A couple of them are the actual solution parts, and they will be covered in the next episode, the next installment. Next, we have this NES header. This is a little different from most NES headers you see because it has two 16 kilobyte prog ROMs, well, two blocks of 16 kilobytes of prog memory, and no char ROM. This targets my one chip Pico single chip cartridge solution, which has no char RAM or char ROM built into it, but remaps half of the console's PPU memory as char RAM. So I get 1 kilobyte to use. Moving on, we have our vectors. This is standard boilerplate for 6502 ASM. And most of this code comes from a NES Hacker program that I started learning from. And it's very commonly the same for every program. So, yeah. Then we have our reset vector. Let's move down a little bit more. We have our reset vector, which is standard, disabling RQs, disabling decimal mode, disabling the APU, which is the audio processing unit, not auxiliary processing unit. Setting up stack, disabling NMI, rendering, and DMC. And we wait for the first vertical blank. Clear the character RAM next. Normal. Oh, not clear the character. Clear the RAM next. Is normal. Second vertical blank wait. And PPU is ready to go. We set up our DMA. We load the palettes. The palettes will be at the bottom. I remember if I boink. Yep, there's my palettes at the bottom. Right. And we load the palettes. We clear the name table memory. This is something that in most of the tutorial code that I saw for program for the NES, you don't really see a name table clearing routine because most people are coding for an emulator, which usually starts with the memory in a known state, a cleared state, while the console itself starts with the memory in a random state. Anything can be in there. It could be in any order. So if you don't clear the name table memory, you end up with junk all over the screen. That's just life. Next, I have a tile loader routine. These are my includes and drawing in the background. And when we start the main. Now, we have a redundant counter set up at the start of my main. I shouldn't need it there. That's alright. Next we enable the rendering. as normal, and then we enter our main loop, this forever loop, where we're just checking the joypad. Let's go down a little bit more as well actually. We read the joypad in, we check if it's an A button is being pressed. If the A button is pressed, right, we go to run the day, and if not, we just keep looping that. Now, probably the best real practice to do would be to have a VB wait in here, so that you're not like busy waiting this, and it'll be checking for the joypad once per frame rather than hundreds of times per frame, but it doesn't really matter at this point in time. So we go down next, we have our run day, my run day routine here, which we set up the pointer again, but we actually initialize both the pointers this time. Pointer 1, counter 1, counter 2, initialize the two counters, and we have our jumps to the two parts, part 1 and part 2. We have my VB wait here, which is just checking the PP status to see if a certain bit is set, and if it's not, then it just continues in this loop until we get there. Right, next we have the NMI routine, which on this day I'm using the sprites. I'm using sprites to display the result output. So we set up our DMA again, and we read the counters and write them out to the correct locations. Right. Right. That's just fairly standard. You can see that I've got it commented, right? We have the Y position on the screen, the X position for the first character, and the attribute, which sets like which oh, I forgot what the name is. Let's go to the bottom again. Which palette to use, rotation or mirroring, those sorts of things. But done the attribute, and then we loop through loading the values for the counter. Yeah. Here we go. And then for each one, each sprite. Right. We load the position, which was at 55 we did before. Store it. Increment X. So it's going to go to the next position, position 200. Load this one here, which is the output. Each character of the output. Right, and I add 1 to it, which gets the right sprite, right tile, the correct tile. And we store that, and we store the attribute, and we store position, and then we just loop. Well, then we increase the X position by 8, which is the width of the character, and then we loop, basically. And we keep looping it. And then we do exactly the same thing, but a bit further vertically down on the screen for the second counter. And I'll actually show what that looks like in MESN. Looks like this. Right, part 1 in white, part 2 in green. And those are sprites at this point. Later on in the year, I think when I get to day 2 or 3, I change them over to background tiles, which allows me to have more than 8 in a row, because I start to need more than 8 in a row for the results. Alright, so that's the output we get out of the NMI, and that's the end of this part for now. So let's go back. Let's have a look at constants. Is very interesting. We've got most of the PPU registers in there, the two counter addresses. So what I have with the counters is that where I actually store the counters is at address 400 to about 40C, I think it is. And so the count high, that's the high of the address, and these are the two low of the address. And by putting these into certain positions, like around here, by storing these values into certain positions, in memory I can load it as an address and then store the data into those address locations. I don't think I use these temp A, temp X, temp Y, although I should have, because sometimes you need to shuffle around the contents of your registers, and it's not always opportune to put them onto the stack and pull them off again. Sometimes it's better just to put it into a memory location. At least that's what I think. Alright, let's have a look at the more interesting one, this counter. So my counters, as you can see, are missing there. I think they are 6 long. 6 long, I think. Let's pull that back up again. Yep, 6 digits long. So we initialize it with Y5, which is a +5, and we zero out the counters in the initialization. Right. And then we have these increments commands, increment routines here. The first one will increment the ones column, the next one will increment the tens column, the next one increments the hundreds column. We've got this little extra thing here which will zero out the tens when it increments, when it rolls over and increments the hundreds. So if I'm incrementing the tens up and it hits 10, then I need to drop it back to 0 and increment the hundreds. And so that's what this little thing here does. Later on, every single place position has this sort of small zero out routine, but in this first day only the hundreds has it. The only hundreds needs to have it separate because I'm only manually inputting values into the ones and the tens positions. So that's just a small thing. Right, we go up to hundreds of thousands in these counters. Later on I have to go much further. So put out that. Next one, not a very interesting one. Clearing the name tail memory. Very simple. Couple of loops just to go through all the memory location, or all the memory area that needs to be cleared up. So let's go back. Next one is tile loader. This one here is very not very simple. It's basically an example of how to load data into CharRAM, and slightly altered to ensure that we only go up to 1 kilobyte and not more. I think it's the default example on NES Dev. And here's my tile data, which will include the data here. And the last one here is setting up the background where you see all the text, which I'll show one more time. Like the day 1, part 1, part 2, the grey areas. So we talk to the PPU again. We store some things in the address where we're going to start storing data, right? And we store all this data in. Here we see the day title. Everything's offset by 1, so E is D, B is A, so DA, and Y is, I assume, 23 in hexadecimal. And space is 1. Right. So we have all the titles in here. And then later on, later on we don't have to put the zeros for the output data into this file, but it all becomes background. And there's one more thing I want to show. One more thing. We'll go to the end. My input I include in this bin file. The input is still in ASCII. It is still an ASCII representation. The only thing I've changed is converting the new lines or character returns to null characters so that I can easily detect the end of lines. Now, what I probably should have done is left them as new lines and you added a 0, a null character at the very end of the input to signify the end of the file, the end of the input, and just looked for the new line characters themselves to end lines. As it is, the way I did it here, I was manually entering the size of the inputs into my code, which worked, but it was a little bit more effort, and it did make it a little bit less compatible with potentially with other inputs. But it worked, it's alright. I just wouldn't do it the same if I was doing it again. Right, so that's the end of this first part. Next time we'll go over the code of solution number 1 itself. So I hope to see you again.